So this is problem 3 of quiz 1 of spring 2010. The problem itself is just a little bit tricky, especially because of the wording and because we're dealing with a slightly different kind of way of thinking about things. We're more in the analog kind of deal. So first of all, if we read through the problem very quickly, we'll see that there's a block right here that we want to sort of characterize. This table here is very important. It's talking about the sum of the voltages. So VA and VB are not, we haven't really specified what they could be yet, but we're more concerned right now with the sum of the voltages. So if we have a 1 volt output if the sum is greater than 4 volts and 5 volts if it's less than 3, and it's between 0 and 5 volts inclusive otherwise. So the first problem asks, suppose constant voltages are applied to the VA and VB input terminals of the Q module and an output voltage of 5 volts is measured at VC after 20 nanoseconds. Assuming that the Q module obeys the above specification, what can you conclude about the sum of the voltages? So I ask you to choose the best answer. Now, the best answer here, if you look at the fact that this is an inclusive value here in this otherwise statement, it could be 5 volts. So the best answer is actually C2, because if VA and VB are less than or equal to 4 volts, then we are just below this first constraint here, because that requires it to be strictly greater than. So we could theoretically have a 5 volt output here. So our best conclusion, therefore, is C2. Okay, so part B of the problem asks, you begin by exploring configurations of the Q module that perform as an inverter. And so there are 2 proposals here. The difference between the proposals is quite simply that one of them has only a single terminal, A. The other terminal is fixed as, well, they're both 2 terminals, but the other terminal is fixed at 0 volts. The other proposal says that A is fed into both input terminals of the device. Now, we want to select the proposal which gives us the best noise immunity and specify some parameters for the logic mapping. What would be our OL, our IL, our IH, and OH, and we need to specify the noise immunity for this. So the difference between these 2 proposals is a little bit subtle, but basically what's going on here is that with the first one, since this is fixed at 0, A can have some degree of noise in it. This 0 here has, we assume, no noise. It's just tied directly to ground. This other case, the A is being fed into both terminals, so both terminals will have some kind of input noise. So what we would expect is just quite that simply that the noise for each signal would have to be half as much. So let's look at the table again from the previous part of the problem. We can see that VA plus VB less than 3 volts will allow us to have a value that's right here of 5 volts output, a high output, and a 1 volt output if VA plus VB is greater than 4 volts. So on proposal 1, our VIL can be 3 volts. Reason being is that as long as, see, VB is always going to be 0, and so VA can be anywhere between 0 and 3 volts in order to get this 5 volt output. The VIH then is quite simply 4 volts. Again, the reason being that VB is going to be 0 volts, and VA is going to be anywhere between 4 and above. So therefore, our final value here for proposal 1 are these 2 values. Now with proposal 2, it's a little trickier, because each terminal can have the noise, and if we assume it's coming from the same signal, so each one can only have half the amount of noise. In this case, VIL for proposal 2 is only going to be 1.5 volts, and VIH will only be 2 volts. Because if we have to think of the worst case scenario, for example, where VIL of terminal, the input value of A is 1.5 volts exactly. And so if we have the noise we have noise, then the total sum, if it's if it were any higher than 1.5 volts, we couldn't guarantee that the output is going to be 5 volts from the system. So our best proposal here is 1. The values for OL and IL and IH and OH, well, we've already found IL and IH, so let's put those in there. Now, from the table above, we remember that the low output would be 1 volt if our sum of the voltages, which is just A in this case, is greater than 5, and OH will be 5 volts. So what's our noise immunity here? Noise immunity, remember that if we have this simple diagram here, this is OL, this is IL, this is IH, and this is OH. Our noise immunity is this value here, so it's simply VIH minus VIL, which is just 1 volt. Alright, so now for the last part of the problem. Consider a logic convention for which a Q module can serve as a logic device computing an interesting, some kind of non-constant function of its inputs, which maximizes the noise immunity. So you'll notice here that now we're using 2 terminals separately. We have A and B. So what really this matches the proposal 2 case, in which we can't guarantee the noise for either one like we could with proposal 1, where that would just be 0. So we have to follow the same discipline here, where VIL is 1.5 volts and VIH is 2 volts. So the noise immunity here is now just 0.5 volts. And this guarantees that we will fall in the ranges of the problem was specified back in the way up here. Now you'll notice there's a part D here. This was actually stricken from the exam because it actually turns out to be an incorrect problem. So don't worry about that one.